One of the most important things you need to understand in order to write Plutus smart contracts is the accounting model that Cardano uses. And that is the so-called EUTxO model, which is an abbreviation for Extended Unspent Transaction Output Model. The EUTxO model, without being extended, is the one that has been introduced by Bitcoin. But there are other models. Ethereum, for example, uses a so-called account-based model, which is what you're used to from a normal bank, where everybody has an account and each account has a balance. And if you transfer money from one account to another, then the balances get updated accordingly. But that is not how the EUTxO model works. Unspent transaction outputs are exactly what the name says. They are transaction outputs, that is outputs from previous transactions that happened on the blockchain that have not yet been spent. So let's look at an example where we have two such EUTxOs. One belonging to Alice, 100 ADA, and another one belonging to Bob, 50 ADA. And as an example, let's assume that Alice wants to send 10 ADA to Bob. So she creates a transaction. And a transaction is something that has inputs and outputs. Can be an arbitrary number of inputs and an arbitrary number of outputs. And an important thing is that you can always only use complete EUTxOs as input. So if she wants to send 10 ADA to Bob, she can't simply split her existing 100 ADA into a 90 and a 10 piece. She has to use the full 100 ADA as input. So by using the EUTxO of 100 ADA as input to a transaction, Alice has now spent that EUTxO. So it's no longer a EUTxO, it's no longer unspent, it's been spent. And now she can create outputs for a transaction. So she wants to pay 10 ADA to Bob. So one output will be 10 ADA to Bob. And then she wants her change back. So she creates a second output of 90 ADA to herself. And so this is how, even though you always have to consume complete EUTxOs, you can get your change back. So you consume the complete EUTxO, but then you create an output for the change. And note that in a transaction, the sum of the input values must equal the sum of the output values. So in this case, 100 ADA go in and 10 plus 90 ADA go out. This is strictly speaking not true. There are two exceptions. The first exception is transaction fees. So in the real blockchain, for each transaction, you have to pay fees. So that means that the sum of input values has to be slightly higher than the sum of output values to accommodate for the fees. And the second exception is the native tokens that we have on Cardano. So it's possible for transactions to create new tokens, in which case the outputs will be higher than the inputs, or to burn tokens, in which case the inputs will be higher than the outputs. But that is a somewhat advanced topic, how to handle minting and burning of native tokens in Plutus, and we'll come back to that later in the course. So for now, we'll only look at transactions where the sum of the input values equals the sum of the output values. So this is a first example of a simple transaction, and we see that the effect of a transaction is to consume unspent transaction output and to produce new ones. So in this example, one EUTxO has been consumed, Alice original 100 ADA EUTxO, and two new ones have been created. One 90 ADA EUTxO belonging to Alice and another 10 ADA EUTxO belonging to Bob. It's important to note that this is the only thing that happens on a EUTxO blockchain. The only thing that happens when a new transaction is added to the blockchain is that some former EUTxOs become spent and new EUTxOs appear. So in particular, nothing is ever changed. No value or any other data associated with a transaction output is ever changed. The only thing that changes by a new transaction is that some of the formerly unspent transaction outputs disappear and others are created. But The outputs themselves never change. The only thing that changes is whether they are unspent or not. Let's do one other example, a slightly more complicated one, where Alice and Bob together want to pay 55 ADA each to Charlie. So they create a transaction together, and as input, Alice has no choice. She only has one EUTxO, so she uses that one. And Bob also doesn't have a choice because neither of his two EUTxOs is large enough to cover 55 ADA. So Bob has to use both his EUTxOs as input. This time we need three outputs. One, the 55 plus 55 equals 110 ADA for Charlie, and then two change outputs. One for Alice's change and one for Bob's change. So Alice paid 90, so she should get 35 change, and Bob paid 60, so he should get 5 change. One thing I haven't yet explained is under which conditions a transaction can spend a given EUTxO. Obviously, it wouldn't be a good idea if any transaction could spend arbitrary EUTxOs. If that was the case, then Bob could spend Alice's money without her consent. So the way it works is by adding signatures to transactions. So for our first example, our transaction 1, because that consumes an EUTxO belonging to Alice as input, Alice's signature has to be added to the transaction. And in the second example, because there are inputs belonging to both Alice and Bob, both Alice and Bob have to sign that transaction, which incidentally is something you can't do in Daedalus. So you would have to use the Cardano CLI for complex transactions like that. Everything I've explained so far is just about the EUTxO model, not the extended EUTxO model. So this is all just a simple EUTxO model. And the extended part comes in when we talk about smart contracts. So in order to understand that, let's just concentrate on one consumption of a EUTxO by an input. And as I just explained, the validation that decides whether the transaction that this input belongs to is allowed to consume that EUTxO in the simple EUTxO model relies on digital signatures. So in this case, Alice has to sign the transaction for this consumption of the EUTxO to be valid. And now the idea of the extended EUTxO model is to make this more general. So instead of just having one condition, namely that the appropriate signature is present in the transaction, we replace this by arbitrary logic. And this is where Plutus comes in. So instead of just having an address that corresponds to a public key and that can be verified by a signature that is added to the transaction, instead we have more general addresses that are not based on public keys or the hashes of public keys, but instead contain arbitrary logic that can decide under which condition this specific EUTxO can be spent by a transaction. So instead of an address going to a public key, like Alice's public key in this example, there will be an arbitrary script, a script containing arbitrary logic. And instead of the signature in the transaction, the input will justify that it is allowed to consume this output with some arbitrary piece of data that we call the redeemer. So we replace the public key address, Alice in our example, by a script, and we replace the digital signature by a redeemer, which is an arbitrary piece of data. Now the next question is, what exactly does that mean? What do we mean by arbitrary logic? And in particular, it's important to consider what information, what context the script has. So there are several options. And the one indicated in this diagram is that all the script sees is the redeemer. So all the information the script has in order to decide whether it's okay for the transaction to consume this EUTxO or not is looking at the redeemer. And that is the the thing that Bitcoin incidentally does. So in Bitcoin, there are smart contracts. They are just not very smart. They are called Bitcoin script. And Bitcoin script works exactly like this. So there's a script on the EUTxO side and a redeemer on the input side. And the script gets the redeemer and can use the redeemer to decide whether it's okay to consume the EUTxO or not. But that's not the only option. We can decide to give more information to the script. So Ethereum uses a different concept. In Ethereum, the script basically can see everything, the whole blockchain, the whole state of the blockchain. So that's like the opposite extreme of Bitcoin. Bitcoin, the script has very little context. All it can see is the redeemer. In Ethereum, the scripts, the Solidity scripts in Ethereum can see the complete state of the blockchain. So that enables Ethereum scripts to be much more powerful. So they can do basically everything. But it also comes with problems. Because the scripts are so powerful, it's also very difficult to predict what a given script will do. And that opens the door to all sorts of security issues and dangers, because it's very hard to predict for the developers of an Ethereum smart contract what can possibly happen, because there are so many possibilities. So what Cardano does is something in the middle. So it doesn't offer such a restricted view as Bitcoin, but also not such a global view as Ethereum, but instead chooses a middle way. So the script can't see the whole blockchain, can't see the state of the whole blockchain, but it can see the whole transaction that is being validated. So in contrast to Bitcoin, it can't just see this one input, the redeemer of this one input, but it can see that and all the other inputs of the transaction and also all the outputs of the transaction and the transaction itself. And the Plutus script can use that information to decide whether it's okay to consume this output. Now in this example, there's only one input, but if this transaction had more than one input, then the script would be able to see those as well. There's one last ingredient that Plutus scripts need in order to be as powerful, as expressive as Ethereum scripts, and that is a so-called datum, which is a piece of data that can be associated with a EUTxO in addition to the value. So at a script address, like in this example, in addition to this 100 ADA value, there can be an arbitrary piece of data attached, which we call datum. And with this, we can actually mathematically prove that Plutus is at least as powerful as Ethereum. So everything, every logic you can express in Ethereum, you can also express in this extended EUTxO model that Cardano uses. But it has a lot of important advantages in comparison to the Ethereum model. So for example, in Plutus, it is possible to check whether a transaction will validate in your wallet before you ever send it to the chain. So something can still go wrong. So for example, your transaction can consume an output, and then when it gets to the chain, somebody else has already consumed that output. This output has already been consumed by another transaction. You can't prevent that. But in that case, your transaction will simply fail without you having to pay any fees. But if all the inputs are still there that your transaction expects, then you can be sure that the transaction will be validated and that it will have the effect that you predicted when you ran it in your wallet. And this is definitely not the case in Ethereum. In Ethereum, in the time between you constructing a transaction and it being incorporated into the blockchain, a lot of stuff can happen concurrently, and that's unpredictable. And that can have unpredictable effects on what will happen when your script eventually executes. So that means in Ethereum, it's always possible that you have to pay gas fees for a transaction, although the transaction eventually fails with an error. And that is guaranteed not to happen in Cardano. In addition to that, it's also easier to analyze a Plutus script and to check or even prove that it is secure, because you don't have to consider the whole state of the blockchain, which is unknowable. You can concentrate on this context that just consists of the spending transaction. So you have a much more limited scope, and that makes it much easier to understand what a script is actually doing and what can possibly happen or what could possibly go wrong. So this is it. That's the extended EUTxO model that Plutus uses. So to recapitulate, in extending the normal EUTxO model, we replace public key addresses from the normal EUTxO model with scripts, Plutus scripts, and instead of legitimizing the consumption of EUTxO by digital signatures, as in the simple EUTxO model, arbitrary data, that's called redeemer, is used on the input side. And we also add arbitrary custom data on the output side. And the script, as context, when it runs, sees the spending transaction, the transaction 1 in this example. So given the redeemer and the datum and the transaction with its other inputs and outputs, the script can run arbitrary logic to decide whether it's okay for this transaction to consume the output or not. And that is how Plutus works. One thing I haven't mentioned yet is who is responsible for providing datum, redeemer, and the validator, the script that validates whether a transaction can consume an input. And the rule in Plutus is that the spending transaction has to do that, whereas the producing transaction only has to provide hashes. So that means if I produce an output that sits at a script address, then this producing transaction only has to include the hash of the script and the hash of the datum that belongs to this output. But optionally, it can include the datum and the script as well, fully. But that's only optional. And if a transaction wants to consume such a script output, then that transaction, the spending transaction, has to include the datum and the redeemer and the script. So that's the rule how it works in Plutus, which of course means that in order to be able to spend a given input, you need to know the datum, because only the hash is publicly visible on the blockchain, which is sometimes a problem and not what you want. And that's where this optional possibility comes in to also include it in the producing transaction. Otherwise, only people that know the datum by some other means, not by looking at the blockchain, would be able to ever spend such an output. So this is the EUTxO model, the extended unspent transaction output model. And that is, of course, not tied to a specific programming language. I mean, what we have is Plutus, which is based on Haskell, but in principle, you could use the same concept, the same EUTxO model with a completely different programming language. And we also plan to write compilers from other programming languages to Plutus script, which is sort of the assembly language underlying Plutus. So this extended EUTxO model is different from the specific programming language you use. In this course, we will use Plutus, obviously, but the understanding the EUTxO model is independently valid from understanding Plutus or learning the Plutus syntax.